7.3 Identities and Algebraic Transformation of Expressions. Your essential question is, given a trig expression, how do you transform it into an equivalent expression whose form is simpler or more useful? So a lot of times you'll be given a trig expression, but it's not going to be useful to you, and maybe you can use some of your other identities or some of the other properties or like the quotient properties or the reciprocal properties to make it into a form that's more useful. Other times you're going to have to prove, for example, that two sides of an equation are actually equal to each other. And so you're going to want to really know your trig properties and your trig identities and be able to transform them into anything that you could possibly think of. This will become more easy as you practice it, I promise. So let's just think of example 1. You're going to transform sine x cotan x into cosine x. So I'll start with sine x cotan x. And I know that cotan x is the same thing as cosine x over sine x. So I can see now that these things are going to reduce, and sometimes you're going to have to play with this. Maybe you wanted to, I don't know, change sine into like 1 over cosecant, right? Maybe you just have to kind of play with these sometimes. And there's something in your textbook that I'll show you in a few minutes that really gives you kind of like a strategy, a plan, okay? But this basically ends up giving us cosine x. Therefore, we can say that sine x cotan x is equal to cosine x. Let's try another one. So example 2. We're going to transform cosine squared x minus sine squared x into 2 sine squared x. So I notice that, I start here with a cosine and a sine, and I basically want to get rid of the cosine. So I need to be thinking to myself, what's another way to write cosine squared? And you might want to think to yourself, that Pythagorean identity, this is going to come up a lot. So I can say, well, cosine squared is really the same thing if I subtract sine squared from both sides as 1 minus sine squared x. So how about instead of having cosine squared x, I plug in 1 minus sine squared x. Okay, so I'm going to take cosine squared x minus sine squared x. And I am going to, instead of having cosine squared x, I'm going to take this value and plug it in right there, substitute it in. So I've got 1 minus sine squared x minus sine squared x. And just think of these as like x's, right? If I were subtracting an x and subtracting another x, those are like terms. I can combine them to subtract 2 x's. Well, I'm subtracting a sine squared x and another sine squared x, so I'm subtracting 2 sine squared x's. So this becomes 1 minus 2 sine squared x, which is exactly what you're trying to transform it into, 1 minus 2 sine squared x. Therefore, we know that cosine squared x minus sine squared x does in fact equal 1 minus 2 sine squared x. Let's talk about what an identity is. An identity is basically when both sides of an equation represent identical numbers for all values of x. Basically, an identity is a true equation. Now, to prove that a trig equation is an identity, let's see. We're going to start with the expression on one side of the equation. And then you try, so you don't try and work on both sides at the same time. You try and just work on one side, and you try and get that one side to look like the other side. So start with the expression on one side of the equation and transfer into the other, or transform into the other. Now, you can't prove an identity graphically or numerically. You have to prove it algebraically. But you can confirm it this way. You can confirm that it works graphically or numerically, but you want to prove it, you actually have to do the algebra associated with it. So let's do example 3. We're going to prove that 1 plus cosine x times the quantity 1 minus cosine x equals sine squared x. So what I'm going to do is I'm probably going to work with this side and try and make this side into sine squared x. So here's my proof. And I'm just going to take basically this side right here. I'm going to take 1 plus cosine x and multiply that by 1 minus cosine x. And I'm trying to get this side to look like that. So I see two binomials, so I'm going to go ahead and double distribute. It's also a sum and difference pattern, so the inners and the outers are going to cancel out, and you're just going to be left with the first and then the last. And then what did we say in our last notes? I think we did that for cosine. Let's see, where did we put that? We said that if we took that cosine squared x would basically be 1 minus sine squared x. So instead of having cosine squared x, I'm going to put 1 minus sine squared x. So when I do that, I get 1 minus 1 plus sine squared x. Those go away, and I'm just left with sine squared x. So that worked, and so now I can say that the quantity 1 plus cosine x times the quantity 1 minus cosine x is in fact equal to sine squared x. Showing it by proving it, right? Okay, that was example 3. Let me find another piece of paper. Let's do example 4. Actually, maybe at this point it might be a good time to take a break and look in your textbook. So, let's see. 7.3, there is a great procedure. This is on page 354. So on page 354, it basically has a procedure transforming trig expressions and proving identities. So, and I would read through this. I'm not going to read all of this to you, but basically, obviously write the given expression or identity, but then pick a side of the equation that you wish to start with and write that down. Okay, and usually they say that it's easier to start with more complicated side. Then you're just going to think to yourself, what are some algebraic things that I can do? Right? You can, like for example, in the last one, we double distributed. Okay, maybe you're going to have to factor. These get kind of crazy too. Watch, we'll start factoring some of these things and it'll be a lot of fun. Okay, so think about any algebra that you can do. And then you're going to look for, after you've thought about all the algebra that you can do, like factoring things out, you're going to look for trig things to do. So you want to think about, you know, for example, you know that tangent is sine over cosine. So sometimes instead of using tangent, you're going to want to use sine over cosine. Definitely think about your Pythagorean properties. Okay, those are from your last lesson. And I would write those all down and have those with you. Try and reduce the number of different functions by making them into easier ones. Okay, and keep looking at the result and thinking of ways you can get closer to it. So that's basically, these are some great guidelines to go by, and I would reference this. Back to example 4. We're going to prove algebraically. Here, let me write it over here. Cotan of A plus tan of A equals cosecant A secant A. So right away I think to myself, well, cotan and tangent, I can rewrite those in terms of sine and cosine. And sine and cosine become, also their reciprocals are cosecant and secant. So I know it has something to do with that. So I'm going to mess around with the left-hand side and see if I can get it to look like the right-hand side. So here's my proof. I'm going to start with cotan of A plus tan of A. And I know that cotan of A is cosine A over sine A. And I know that tan of A is sine A over cosine A. Now, can I add those together? No, we need common denominators. So my common denominator would be sine A, cosine A. So I need to make these have common denominators by multiplying top and bottom by the same thing on both sides, but different on both sides, right? And look what I'm getting now. So now I have cosine squared A plus sine squared A all over sine A cosine A. Well, what is cosine squared A plus sine squared A? Hopefully that's reminding you of that trig identity, the Pythagorean identity. So that becomes 1 over sine A cosine A. Well, I want to make it look like this. So I need some cosecants and some secants. Well, really, sine A, so I'll leave the 1 on top. Sine A is 1 over cosecant A, right? Because they're reciprocals of each other. And cosine A is 1 over secant A, again, reciprocals of each other. So if you think about this, you really have 1 divided by this, or we're going to multiply by the reciprocal of that, which is cosecant A times secant A, and that's all over 1. So I'm left then with cosecant A times secant A. So, and that's exactly what I was trying to get. Therefore, I can say that cotan A plus tan A is the same thing as cosecant A times secant A, and I proved it. Now, in your book, I can't remember what it means. QED, let's see. So when they're doing these, and I've done the exact same examples as in your book, when they're doing these, oh, they're not. Oh, yeah, they are. They're using this QED. That's Latin for something. And I went into the index and I found it. It's on page 41. And this was the first time we ever saw the QED, and basically it's Latin words, quod erat demonstratum, meaning which was to be demonstrated, or basically that's how you kind of end a proof, like we proved it. Okay, and also in case if you don't believe me that the 3 dots mean therefore, there it is. Okay, moving on to our last example. So we're once again going to prove algebraically that 1 minus cosine of b over sine of b equals sine of b over 1 plus cosine of b. Well, I'm thinking to myself, when I say something like 1 plus cosine b, I think to myself of like conjugate pairs. And that was always a way that we were able to help ourselves simplify fractions when we were dealing with like radicals, or when we were dealing with complex numbers. So we can do the same thing here. So I think I'm going to start with this side, and I'm going to try and turn it into this side. Okay, so here's my proof. I'm going to start with sine b over 1 plus cosine b. And I'm going to multiply numerator and denominator by the conjugate of my denominator. So this is like a conjugate binomial. And when I do that, what ends up happening is I'm just going to end up with like cosine squared b here. Okay, so I'm going to end up with sine b times the quantity 1 minus cosine b over, that's going to give me 1 squared, which is 1, and then the inners and outers reduce out. Okay, that's the whole reason that we do this, right? We multiply basically a sum and difference pattern here. And then that is subtract cosine squared b. Now what's 1 minus cosine squared b? Hopefully you're getting the hang of this, because cosine squared plus sine squared equals 1. So it would make sense that sine squared would be 1 minus cosine squared. So I have sine b times 1 minus cosine b all over sine squared b. And now I have factoring that I can do, right? I can reduce top and bottom by the common factor of sine b. So this becomes 1, and then this just becomes a sine b. So I'm left with 1 minus cosine b over sine b, which is exactly what I wanted. Therefore, I know that 1 minus cosine b over sine b is the same thing as sine b over 1 plus cosine b. And you're more than welcome to use QED to show that you proved it.